This question is not as simple as what we've seen in the past with just putting an acid into water and wanting to know what the resultant pH is, or putting a salt like sodium acetate into water and wanting to know what the pH is. No, this question is a little bit harder, and if you sort of enjoy these problems that are more challenging, you might just be a chemistry major in the making. It's kind of, how would you say, sadistic almost to like these. They're just weird, but they're a challenge, and so in some way they are kind of fun to figure out. There's two parts when you always have these problems where you have an acid and base reacting in water before you talk about the pH of the water. So you kind of want to split those parts in half, or I guess say I'm going to do this part first, look at the acid-base reaction they talk about, and then look at maybe determining the resultant pH of that solution. So sometimes they'll talk about how much of the acid-base reaction occurred, or they'll say the reaction went to equivalence point. What that means is that the acidic protons, the number of those is equal to the hydroxides within the base, or the acetates within the base. The negatives cancel the positives. You came to a perfect equivalence point. So let's look at the reaction they give us. So first of all, it's saying that we have some sodium acetate. So we know sodium acetate, I guess the formula looks something like this, CH3COO minus, and it's counterbalanced by the sodium's positive charge. But because this is a spectator ion, I'm just going to cross it out and say I'm just worried about the acetate. And it's titrated to equivalence point, meaning there's going to be, for every one of these, there's going to be one proton with sulfuric acid. Now, right out of the gate, you want to notice, I do have a situation. The sulfuric acid has 2 acidic protons. So I'll need twice as many of these, because for this 1 mole, I get 2 acidic protons. So we'll balance that here. We know that we're going to consider equivalence points, so we're taking every one of these and making one of these. And we're going to have left the sulfate anion minus 2. So I need to balance some things. I know it's going to take, again, 2 of these to react for every one of these, because there's going to be 2 protons that need to come on. There's one spot here, and then we have to get another one. So in the end, I'm going to have 2 and 2. It's going to change things a little bit, but we've got it now covered, the balanced equation. Now, I'm not going to use the ICE table here because they tell us that we're at equivalence point. So what I'm going to do is say, I'm going to determine the moles of this, and we'll use the balanced equation to know what moles of sulfuric acid is needed. So the first thing I do is to take the molar amount, 0.857. I know molarity times volume in liters is equal to moles. So in this box, I'm going to put what the moles are going to be for sodium acetate. How do I do that? I multiply the molarity times the volume, which has got to be in liters. So we're going to say 0.1005, because you move the decimal place over 3 places to get to liters, times the 0.857, and we know for sure that I have 0.086, we'll say 1 moles of this sodium acetate. And it's titrated to equivalence point, meaning that we need to have the, number of these protons equal to this number. Well, for every 1 sulfuric acid, I get 2 protons. So I'm going to cut this in half and say that's going to be the number of moles of sulfuric acid I need, this divided by 2. And you can do that thing we did in Gen Chem 1, where if I'm leaving this acetate, I divide by the coefficient I'm leaving, and I multiply by the coefficient I'm going to have a perfect neutralization of every anion with the acid. That is what equivalence point means. I need to take this number and divide it by 2. So we get 0.04305. We'll keep it there. So now we know the moles of sulfuric acid. So what we're going to be able to do, I'm going to use this space here just so I can keep a little bit of this space here. We're going to be able to say the 0.04305 is equal to, going backwards, the 1.5 molarity times this unknown volume in liters. So I'm going to divide the 0.04305 by the 1.5 molar, or 1.5, and that gives me X is equal to 0.0287. I move the decimal place over 3 places, and that would be 28.7 mils. So we just solved the first problem. I need, to get to equivalence point, 28.7 mils of the sulfuric acid to completely neutralize the weak base. And just remember, weak bases are usually titrated with strong acids, and weak acids are usually titrated with strong bases. You don't want to titrate a weak acid with a weak base. So when we're titrating, we typically titrate strong or weak acids with a strong base. And the other way around, for if we have a weak base, we titrate with a strong acid. Hey, we need to move on to the next question, which is going to require an ice table and sort of a new after equivalence point, I guess, reaction. We know this, that the acetic acid that's generated because of this reaction would be 0.0861. You say, well, how'd you know that? Because again, these reacted and all of it reacted. And so 2 of these makes 2 of these. So if it's 0.0861, I multiply by 2, divide by 2, it's the same number. So I'm going to start off with, now, because I'm considering like after the equivalence point is reached, I have this acetic acid in water, 0.0861 moles of it. And it's going to form, because it's a little bit of acidity, we're going to form a little bit of the conjugate base back plus the H3O plus. If I want to know pH, I need to know what that H3O plus is, whatever small degree. So we'd say it doesn't matter for this. This will be 0 and 0. We have initial state covered. Our change is minus X. And we're going to say plus X plus X. And now you can kind of see the law of mass action starting to come into play. I can say K for acetic acid, I think it's about 1.8 times 10 to the minus 5th. But we can say that's equal to X squared over 0.0861 minus X, but because the K is so small, we can make that approximation and say 0.0861 is what we have as the amount of, at equilibrium, acetic acid, 0.0861. And of course, since 0 plus X is X and 0 plus X, I just had my products as X squared. Now I'm using moles, and I need to be careful. I did it again. Doggone it. I used mole values here. So I'm going to have to change this mole value of 0.0861 into molarity. You cannot use mole values in your law of mass action, I guess, unless the volumes cancel out, but they don't here. So what I'm going to do is look back to my solution and just see how much volume I have. We said 28.7. So I'll have that, plus the 100.5. So I need to add that up. I get 129, but that's going to be in liters. I need to make sure that's in mils. I need to go to liters, so I'm going to say 129.2 mils is 0.1292 liters. So that is needing to be done before we use the law of mass action. I need to get that into molarity. I used mole talk here, but had to get it back to molarity. I'm going to stop there, but that gets us all the way down to now just the math. Once we find X, we would find then that's the concentration of H3O plus, and we would take the negative log of that, and that would give us our pH. It's sadistic to like these types of problems, but maybe you're a chemistry major or thinking about it. If you kind of like this problem solving, well, you might just be a chemistry major. Bye bye.